Hi everyone, in this video we are going to see a practical guide to Retrieval Augmented Generation RAG. My name is Abdul Salam and I'm a PyTorch ambassador. So we are going to see what RAG is, why we use it, and the core components of it. We are also going to see when you build a RAG system, how you can use some metrics like precision and recall to evaluate the quality of your system. And we are also going to see some important considerations when you have RAG in production. So the traditional way we use large language model is we have a prompt, we send it to the model, and we get a response, right? But the problem is that data, it's possible that we might have a private data that model was not trained on, and that can introduce an issue of hallucination. You can have a company with a chatbot, and that chatbot has to answer questions regarding your policies, for example, and it's possible that the large language model you are using might not have access to the data or information about your return policy, for example, right, for your customers. Now, what is RAG? Well, from RAG, RAG stands for Retrieval Augmented Generation, as we have seen from the first slide. So retrieval, really, this is the most important part of it. It is where we have a retriever that when you have a prompt, you send in a prompt, the retriever goes into your local database or your knowledge base and gets relevant documents, relevant information about that specific prompt, so that it can be appended to the original prompt and be sent to an LLM. So the retriever returns the top key relevant chunks or data or documents regarding your prompt that are very relevant, so that we can have better context to an LLM. Augmentation kind of is for the fact that when we retrieve those documents, we append them to the original prompt to be sent to an LLM. And generation is for the fact that, okay, the LLM generates a response. Some of the applications of RAG include chatbot, for example. You can have a company that you are selling products, and a chatbot might be answering user questions about returning a particular item, and that chatbot can have access to internal documents and frequently ask questions to help assist users. And it can also be used in personalized assistance. So, for example, an assistant might have access to your calendar event, emails, and messages. And when you ask a specific question, that assistant can retrieve relevant information from your calendar to provide you better answers. So, in general, the more data we give to an LLM, the better. All right, so let's say we have a prompt. How do we retrieve relevant information from our database? Well, an approach that you can use for the retriever is keyword search, right? Using an algorithm like term frequency inverse document frequency. So let's say we might have a prompt, you are building a chatbot, we might have a prompt that is asking what is the return policy for jeans. And first of all, you can build a kind of bag of words for all the words in the input prompt. And you can build a table, so for all of the documents. Let's say I have 3 documents in my database. If that document contain, let's say, return, which is part of the original prompt, you put 1. If that document 2, for example, does not have the word return, you put 0. Document 3 has the word return, you put 1. So essentially, we're building a term frequency. Of course, in reality, in production, you might have thousands of documents. Here we just have 3 documents for simplicity. Next, for example, using this algorithm, we then apply document. Sorry, this should have been inverse document. This is not document frequency, but then apply inverse document frequency to downweigh common words like a, the, is, and upweigh rare words, rare terms that might carry important meanings. And we do that using inverse document frequency. Let's see how it works. So essentially this table that we have here, we are going to update it. So how do we compute the inverse document frequency? Okay, we take the log for a word. For each word, we are going to compute this inverse document frequency. And to do that, we take the log of the total number of documents that we have divided by the total number of documents that have that specific word. So let's say we have 3 documents. I'm going to compute this inverse document frequency for the word genes. We just have to say log of 3. 3 is the number of documents that we have divided by 1. 1 is for the fact that there's only one document that has the word genes. And when we do that, we get 1.099. Okay, so we are just going to go to the original table, and for the row of genes, all of those values, I'm going to multiply them by 1.099. Similarly, you compute the inverse document frequency for policy and multiply that value by values in the row of policy in the previous table, sorry. Then after you do that, you take the summation compute this score and then get the maximum. So in this case, for our prompt, we retrieve document 2 because it has the maximum. So we get top k. In this case, k is 1. If k was 2, we will have retrieved document 2 and document 1 because they are the two, they have the 2 maximum scores. So I'm just giving you this example for simplicity, using less documents and using K1 for example. Well, keyword search actually really used, but there are really more sophisticated keyword search algorithms like BM25, best matching 25. You can go online and learn more about this particular algorithm. A second approach to retrieving document is semantic search. The problem with keyword search, it doesn't capture retrieve documents, relevant documents based on meaning. Let's say we have this input prompt. What is the return policy for genes? We can use a form of embedding. You can use an embedding dictionary. Let's say the embedding of the Q. We have already seen embeddings, by the way. You can check a previous video of mine. So let's say the embedding of our input is this, and you can compute the embeddings of all of the 3 documents that we have. So I'm using the same example. Let's say these are the embeddings of the 3 documents that we have. Next, you just have to maybe apply a kind of metric like cosine similarity between our input Q and all of the documents and get the maximum. So in this case, we retrieve document 2 because it has the maximum using semantic search. Okay, so we retrieve document 2. I know that in terms of semantic search, you can have thousands of documents and you have to really do this semantic search very fast. And you should not be applying this cosine similarity anytime there's an incoming document. So let me show you a simple algorithm that is very fast. So this algorithm starts by building a graph where each node in the graph is a document, and each node connects to few nearest neighbors by vector similarity. So a node is going to be connected with documents that are close to it. Next, let's say we have an incoming document and you want to apply a form of search. Well, you can start any place in the graph, then walk to the neighbor that is more similar to the query, then stop when no neighbor improves similarity. Then return the best k nodes found. Let's see an example. I know that, but that might not be very clear. So this is a sample graph. So all of this A, B, C, D, all of these are documents. So document B is relevant, is actually close to document A, and document K, and document E, and document C. So you might have an incoming document. Let's say you start at a random place. Okay, this is how the algorithm works. We start at E, for example. What you can do is check the neighbors of E and compute the similarity between our input Q and all of the neighbors, and go to the neighbor that has the maximum similarity. So the similarity of QB is this, 0.61. For G it is this, for F it is this. In this case I go to G because it has the maximum similarity. I am at G. I also do the same. I check the neighbors. You compute the Q, the similarity of original prompt Q of K, I, H, and also E. In this case, the similarity of Q and I is the maximum, 0.86. I go there. I'm at I do the same. I check the neighbors of I, which are G and J. In this case, all of the neighbors, the similarity of all of the neighbors is actually less than the similarity of the current node that I'm in. So I actually stop. In this case, I return document I and I say this particular document is the nearest to my original prompt. So I retrieve this document. This is a basic algorithm. One of the disadvantages is that you have to kind of build a graph beforehand. Other fast algorithms that are even more sophisticated include hierarchical navigable small world graphs. Actually, this is also graph based, and inverted file index. You can check them online. I don't want to go into them. Finally, in terms of retrieving documents, there are also metadata filtering, which is important for production. So you might retrieve documents using keyword search and semantic search that particular user should not see. And you should not append those documents to the prompt to be sent to an LLM that could lead to answers that can reveal information that particular user should not see. So that is where metadata filtering comes in. So each document has some metadata information like the theme, the access level, its region also. So let's say these are the documents that we have. This is the theme information. This is the access level metadata. So if that user is a basic user, and let's say we have retrieved 3 documents, we just ignore document 2 and return document 1 and 3. So that is metadata filtering. Okay, we have seen keyword search, we have seen semantic search, and this important metadata filtering. We can really build a hybrid approach. So we start with a knowledge base. We can apply, we might have an incoming prompt. We start with a knowledge base, apply keyword search, retrieve some documents, apply semantic search, we retrieve some documents. From the documents retrieved from keyword search, we apply the metadata filtering. For documents retrieved from semantic search, we apply metadata filtering, then we combine the results. Now, let's say you have built the retriever. How do you evaluate it? What you can do is build a sample data set for multiple prompts and create ground truth and also retrieve documents from the retriever. So let's say for this prompt, you know that for this return policy for genes, you know the ground truth is document 2 and 1. And let's say the retriever got document 2 and 3. And you do for multiple prompts. So you build a small data set, then compute recall and precision at K. Okay, K is the top what document. So recall is like the recall kind of computes how many of the relevant documents did we manage to find, and precision kind of computes how many of the retrieved documents are actually relevant. So recall is essentially total number of relevant documents retrieved in top K divided by the total relevant documents. Precision is like total number of retrieved documents in top K divided by K. Let's see a simple example. Let's say for the sentence return policy for genes, let's say this is the ground truth. Retrieved documents are this, document 2, 1, and 3. Recall is going to be from the previous formula 2/2. Precision at K is 2/3. So let's say the precision or the recall might be low. Depending on your example, you might go back and change maybe the way you implement the keyword search. Maybe you can use a different algorithm, or for the semantic search, you can use a different embedding model, try different things to maybe improve the score. Okay, let's see chunking. You might have documents that are very long and you cannot just send those very large documents append those documents to the original prompts to be sent to an LLM, that could introduce an issue of context length, right? So it's important to split, kind of cut very long documents into pieces so that we are able to manage our context lengths. And also embedding has limits. I don't know how you can embed a very large document. And also we only want to send kind of relevant information to the large language model. If you send a very large text that has so many different parts and different topics, it can lead to confusion. So you can build chunks using really balanced sized. So let's say for a large document, you can create a chunk of from word 1 to 500, from 451 to 950, from 901 to 1400. Okay, so from one document we can get 3 documents. So here we are kind of having an overlap. Let's talk about hallucinations. Well, actually RAG can help us kind of fix the issue of hallucination, but LLMs generate probable text. So as I said, RAG can be helpful, but might not be enough. So some of the defenses is maybe telling the LLM to only make factual claims supported by retrieved context, and maybe requiring citations for sentences and paragraphs. Let's talk about security. There can be issue of unauthorized access to some private data, right? Maybe a user should not see some data. You can introduce a form of authentication, or maybe role-based access control. Okay, so for different roles, they could only have certain document retrieved. Okay, or maybe tenant isolation. So maybe if you have many companies for your product, you can have different storage databases for each company. So essentially, metadata filter might not always be sufficient. And there can be issue that you might be using an API for a large language model. So in this second row, and you might be sending augmented data to the large language model, and once it goes there, might be out of control, right? It might be used to further train that large language model, and you might not want that. In that case, you can use an in-house LLM. And a third issue is, for example, you might build a vector database, and that database could be hacked. And from that embeddings of that vector database, people might attempt to at least recover the original text from that embedding. A solution could be to add some noise transformation to the vectors. Okay. Thank you for watching.